Depending upon your geographical location, good morning, good afternoon, and good evening to the esteemed guest, senior and young participating scientists joining us virtually from different parts of the world. It's a matter of great privilege for us to extend you all a warm and cordial welcome to the second day of the 19th International Online Conference on Mathematical Sciences for Advancement of Science and Technology. In short, we call it MAST 2025, organized by the Institute for Mathematics, Bioinformatics, Information Technology, and Computer Science, having branches in Sweden and Japan. In short, we call this institute as IMBIC. Today, we are going to start the technical session. We begin by commemorating the birth anniversary of Srinivasa Ramanujan, one of the India's greatest mathematical genius. It is indeed a special day in India as it is celebrated annually as National Mathematics Day. Born on this day in 1887, Ramanujan, despite having limited formal education, made profound contributions to number theory, mathematical analysis, infinite series, and continued fractions during his brief yet remarkable life, which ended at the age of only 32. His notebooks, filled with thousands of theorems and formulas, many of which were previously unknown to mathematical world, stand a testament to his extraordinary talent. In 2011, on his 125th anniversary of his birth, the Indian government declared that 22nd December will be celebrated every year as National Mathematics Day. Today, as we celebrate Ramanujan's legacy, let us remember his unwavering dedication to mathematics and his ability to think outside the box. Let us strive to cultivate a love for mathematics in ourselves and in the younger generation, encouraging them to explore the beauty and the wonder of this fantastic subject. With this hope, we start the technical session 3 of day 2 of our conference. The session is about the workshop on data science, accelerate your career. We are fortunate that among us we have a special guest, Shumon Pal. Shumon Pal is a data scientist and AI practitioner for more than 18 years of experience. Currently, he serves as the AI/ML Decision Science Manager at Accenture, where he leads AI and ML interactive sessions and all. So today, he is going to have a session with us, and I'm sure that all of you are eagerly waiting for him. So now, without any further ado, it's my great pleasure to welcome Shumon Pal. Shumon, the session is yours.
Thank you, Abhishek sir. Thank you everyone for joining the sessions. And it's my privilege to be part of these sessions. So today we are going to discuss about optimization techniques, how mathematics are being used in different data science areas, and what kind of problem that we face in our day-to-day life, and how we convert that problem into mathematical problem and then finally solve it. So I'll start with very basics of mathematics, and then we'll try to give some example from academics, and then finally how we can solve those kind of problem, hypothetical problem in real world scenario. I'll share my screen. So I'll start with quick.
Yeah, your screen is visible. Yeah.
Okay. Thank you. So I'll start with quick brief, like what kind of problem we see in day-to-day life in terms of optimizations areas. So like all the constraint-based scenarios in different areas. Like for student, if they need to complete some project within certain time periods. For corporate, improve revenue for certain months. For common man maybe need to buy some home essentials within their budgets of maybe 5K per month or whatever it is. So this is the target that we see in our day-to-day life. However, what we try to do in this target, we want to maximize the outcome score marks for the student. For corporate, we want to maximize the sales. For common man, we want to maximize the quantity of the essential items within the budget that we have. Here we have the threshold of 20 days. For corporate, maybe 1 month, and then for maybe common man, it's 5K. Within that constraint, how we can maximize the target, that's the objective that we take in our day-to-day life. Moving to a very basic LPB problem, you may already gone through that, but I still want to go through it because if few people from this group has not gone through this, then maybe the consecutive things may not be very much relevant. So I want to give a very easy example here. Like one manufacturer has two types of machines to choose from, type A and type B. At least one of each machine that manufacturer should have so that he can run his business. The cost of the machines are maybe thousands for type A and maybe 1200 for type B. Sorry. $1,200 for type B, and they have the space constant as well. So they need to understand how much space each of the machines will occupy. So 4 meters square will be the space occupancy for type A machine. 5 meters square is the space occupancy for the type B machines. With all those things, we have the limitation as well. What is the limitations? The total cost must not exceed 1,20,000. Sorry, 12,000, and the total floor space availability is 48 meters square. The profit from each of the machines are like 120 rupees for each of the product from machine A and 100 for each of the type B machines, right? So with all those constraints, how we generally solve this problem? So this is very simple problem. We have only two variables here. This can be easily solved using graphical methods, right? So we have this problem which we simplified. Machine A, at least one of machine A, one of machine B is required. Cost for machine A is 1,000. Cost for machine B is 1,200. The total amount that we have is 12,000. The space requirement is this much, and the total space that the manufacturer has is 48 meters square, and the profit is this. So if we simplify this, then the inequality or equality comes like this: 1 1. If we divide the same number to all the components, which is coming as 5 6 and 60, and 3 2 and 24, and the inequality will be like this. The objective function is 120 is the profit from type A machine, 100 is the profit from type B machines. So if I am purchasing maybe X number of type A machine, Y number of type B machines, then 120 into X and 100 into Y will be my total profit from whatever machines I am deploying, right? So which means I need to maximize the profit. If whatever X or Y value is, the sum of 120X plus 100Y should be maximum, or that's the maximization functions or objective functions, which is similar to 6X plus 5Y. Similarly, we have another constant on the cost, 1,000X plus 1,200Y, because I have X number of A machines, Y number of B machines. 1,000 into X will be the total cost for cost to purchase type A machines, and 1,200 into Y will be the total cost for purchasing type B machines, and that should be less than equals to 12,000. So here, if we simplify, so I have a mistake here. But if we simplify it, it will come like 5x plus 6y less than equals to 60. And for the space constant, we have 6m square plus, 6 meter square plus 4 meter square. That should be less than equals to 40 meter square, which is simplified versions of it is 3x plus 2y less than equals to 24. And since we need to have at least one of machine X, A, and one of machine B, so that's why at least X should be greater than equals to 1, Y should be greater than equals to 1. So this is the problem that we have converted into a mathematical, simple linear programming problem. And if we try to solve this using graphical methods, we'll just plot x-axis and y-axis. Since the x and y value is greater than equals to 1, everything will be upper right side of the axis coordinate. And here, if we plot all the points, intersections points, this is how each of the inequality looks like. 5x plus 6y less than equals to 60 will be like this. All the points towards the left side will be satisfying these conditions. That's why this arrow represents that. Another inequality is 3x plus 2y less than equals to 24. All the points left to this line will satisfy this inequality. So another two variables or inequality we have: x greater than equals to 1, y greater than equals to 1. So the entire point is my solution area, feasible solutions. So any points from this will maximize my objective functions, and I need to identify what is that point, and that will be my value for x and y. So if I consider 6x plus 5y, this will be the equation of this straight line. And if I roll this straight line towards right, then it will give the maximum value. If I roll this line to left, it will minimize. It will give the minimum value. So ideally, x equals to 1, y equals to 1 gives the minimum value of 6x plus 5y, which will be 6 plus 5. But if I roll this line towards the right side, this will give the last point before it leaves that feasible solution area, will give the optimal value for x and y. So which is coming as 3 and 7.5. But 7.5 machines purchase is not possible. So we'll consider maybe either 3 and 7 or maybe 3 and 8. Considering that space availability and budget constraints. Ideally, it will be 3 and 7. So this is how we solve linear programming problem, where we need to optimize certain scenarios based on different constants. But this is very simple problem where we have only two variables, right? But in real world, this is not the case. We may need to purchase maybe 100 such machines to run the business, and for each of the machines will occupy different space. The cost of each machines will be different. The profit from each of the machines will be different. So if we try to create that inequality or objective function out of it, it will be multi-dimensional problem which we may not be able to solve using graphical methods. And that's where we need to use some different techniques like simplex algorithm or some other techniques to solve those complex scenarios. And this is how the linear programming looks like in multi-dimensional area. So we will have maybe C1, X1, C2, X2 till Cn, Xn is the objective function. This can be either maximization problem or minimization problem depending on the scenarios. We'll have multiple constant where A1, X1, A2, A11, X1, A12, X2 like that, less than equals to B1 like that. And then we will have we'll convert that LPP problem into simple matrix problem, and then finally we solve it using maybe different algorithms that we have available in the market, or maybe we develop some algorithm to solve that particular problem statement. So if I convert this scenario to solve it using maybe any coding language, we definitely need to convert them into some matrix formats to solve using any algorithm. So here, how this matrix will looks like: the objective function is c1 x1, c2 x2, and cn xn. So this is my coefficient matrix c1 c1 c2 till cn, and x1 x2 all the variable till xn. If I multiply, if I do a matrix multiplications, I will get these objective functions. And subject to my coefficient matrix, x variables, and the constant. So this will this is how the constant matrix will looks like. Okay. So now we saw that simple problem, basic problem, how we converted it into a mathematical problem. We solve it using graphical methods, and also we have seen how we can increase the dimension to maybe n, and then how this can be solved using any algorithm. So now let's consider some problem statement. So this, you may have seen this, and anyone want to guess what this is? So this is basically a timetable, right? So every day in any college, school, any university, we follow some timetable. So each period is having some classes, and for each classes there is a room number mentioned and who is going to take that class, right? So this is a very basic timetable, right? And if I consider this, so we have t number of teachers with different expertise. Each teacher can take maybe n number of classes per day. We have m number of modules to complete by maybe 6 months time. If I consider maybe 6 months is the one semester time, and each class has a specific durations. For this, maybe we can consider 50-minute durations, right? So this is the timetable that we are very much accustomed to it, right? Every year we do some changes on this based on the change on the syllabus, change on the number of modules, change on the faculty, or multiple other factors. But this is also very complex task, right? But let's make this maybe timetable little more complicated, right? How we can make this more complicated? Let's consider one class is for one module or topic, right? So earlier, what was happening? We kept that class duration as 50 minutes, which was constant. But let's make it dynamic. Duration of each class or module is different, varying from 10 minutes to 60 minutes. So one module can take maybe 10 minutes time to complete, or maybe 50 minutes time to complete, or maybe 60 minutes time to complete. Each teacher has a bandwidth, right? So each teacher can, and also they has a different kind of skill sets, right? So one teacher can teach different kind of modules, right? So one maybe module 1, module 7, module 8 can one teacher can teach, other teacher can teach different modules like that. And each module, as I mentioned, that each modules are of different durations. And one day is defined by number of different modules to be completed by that day, right? So module is defined by number of students opted for that module. So we are making it one level more complicated by making it so not all student has opted for maybe mathematics honors or physics honors or chemistry honors. Let's consider each student has the freedom to take maybe 50 modules. That can be anything, right? So maybe module 1, module 7, module 8, someone has selected, right? So, and each day the number of attendance of students are also dynamic, right? So we complicated the simple scenario into multi dimensional dynamic problem now, right? So when the creating timetable itself manually was itself quite complex, we added couple of more number of dynamics component into it to make it more complex, right? So now if we need to create a scheduler or create a timetable for each faculty, for each day, for each student, for each day, right? So now this is quite complex. Here another level of complexity is, so as I mentioned, that for each day we don't know how many students are coming, and each teacher can take class of only 20 students. So if there is 21 student or 22 student, so that require two different classes, right? So one class will have 20 student, another class may have one student or so. So with those many complexity, do you think it is possible to create the timetable in manual way? No, right? But how can I solve this problem? And do we think that this kind of scenario may arise? The answer is yes. So we see those kind of problem in industry in day-to-day life, right? So we have different kinds of work or tasks coming in, and we have different kind of resource work has different kind of skill sets to work on those tasks, right? So if I define this problem statement in a graphical way, so this is how this looks like, right? So we have faculties or teachers who can teach different modules, and they have different kinds of expertise as well. So faculty 1 can take theory class of maybe module 2 and module 5. Faculty 2 can take maybe practical class for module 3 and module 6, where module faculty 3 can take both, right? So with these many complexities, so here I have added one more complexity, is the skills level, right? So earlier we considered all maybe theory class, but here I have considered theory, practical, and both, right? So with all those things, if I need to solve maybe for 200 faculties and maybe 4,000 students, and there are maybe 50 modules or 100 such modules, and every day number of students coming or number of faculties coming is also dynamic, right? So with all those complexity, it is quite difficult to solve using any manual way, right? So how we solve this kind of problem? Here the first things that we do is, this is called a skill matrix. Skill matrix is basically plotting who has the skills of what different kind of task and what kind of expertise they have. So faculty 1 is having theoretical knowledge. The faculty not theoretical knowledge, faculty 1 can take theoretical class, faculty 2 can take practical, whereas faculty 3 can take theory or practical both. So if there is any activity coming for module 3, I'll try to reserve my faculty 3 till the time I am exhausting maybe all other faculty who can take one kind of classes for module 3. Because if I can preserve this faculty 3, if there is any additional requirement coming for practical or theory, both can be taken by faculty 3. So that's where we create a clusters or groups of all the faculties or all the resources that I have by their skill group, and we try to understand what is the number of units or what is the number of resource or supply I have for each kind of groups or cluster, right? So if I consider group 1, all the faculty in group 1 can take theory class for module 2 and module 5, and I have 15 such faculty, right? So if I have demand for 15 faculty of this, I'll be able to satisfy that. But these faculties not only take module 2 or module 5, but there are demand for other module as well, and there are other group who also can take class of module 2, right? And how many such faculties I have, so I'll be able to get that group wise count, or this is the demand, sorry, this is the supply that I have for each of the cluster. So now if I got the count of each skill clusters, now I need to get the demand. What is the demand? So for each of the day, how many student I have, or how many module 1 class requirement I have, based on that I'll create a schedule whether I will deploy maybe one faculty from group 4 for module 1, or maybe 5 faculty from group 1 for module 5, like that. So now moving out from this academic example to the real world example, where we get such kind of problem here, like task 1 to task 8. Here also we consider the similar kind of problem here. So they can do either analysis, they can do review, or they can do something else, and we converted them into a different group, and we have the demand like this. Once we converted that skill matrix to group, and that's where we solve using penalty matrix. And how the penalty matrix is being created, as I mentioned, that we always try to reserve the resource who has the more complex kind of skill sets. There I considered both, right? So both means they can take maybe theory class as well as practical class. Here also considered all the reviewer are having maximum payoff, or maybe maximum weightage, so that they will be deployed at the end of it. So with this, I'll move to Python, how we convert this kind of problem into my Python screen is visible, right? I hope so. Okay, so here what we will do, we'll consider a real world scenario where we have maybe number of employees who can do different kinds of work in their day-to-day life, and they have different demands for each of the day, and the supply is the number of resource that I have with different kind of skill sets. So what I'll do is, sorry, my Python script is still running, so I'll show all the results that we already ran a few minutes back. So here I upload the data that we have received. So what kind of data that I have here, let me quickly show that. Yeah, so this is the this is the demand that we have received for any specific day. So you can see here, so we have different dates mentioned here, and the total number of tasks that we have received. If I try to compare with the examples that we have provided, is the different number of modules that needs to be taught on that specific day. And if we want to go through each module wise breakup, this is how it is. So 59 of task 1, 42 of task 2, like that for maybe for this specific day. Then for third, it's 502, and then maybe we have weekends in between, and then 636 is for the 6th, 7th, like that. And this is the breakup for each different task level requirement. So this is the demand that we have received, but this is the historical demand, right? So as I mentioned that we don't know how many students are going to come on any specific date. So what we need to do in that case, we need to predict future. So we'll do the predictions using maybe Arima or Prophet here. But we'll be using the historical data to understand how the pattern of student attendance, or maybe the historical demand, how the historical demands looks like, and based on that, if we can predict the future demands, and based on that, if we can do some planning. So we have skill sets. What is the skill sets? Skill sets are different resource, and they are what kind of activities they can do for each of the tasks or each of the activities. And AHT is nothing but the average handle time. So if it is a task 1, so here we have mentioned different kind of skill sets: analyst, reviewer, DSC, like that. So analyst is maybe the whosoever is in a very initial days of their job, they can take maybe 40 minutes time to do that job, whereas reviewer is bit experts, so that person will take 30 minutes to complete that task, whereas DSC will take 35 minutes or so. So this is the expertise level of each resource, and this is the time they will take to complete each of those tasks. So 40 minutes for task 1, 35 minutes for task 2, like that. And also we need to consider one thing here is the holidays. So we already have considered the weekends. So no one is going to work on weekends. So we already have excluded that from the data. But in future dates also we need to consider what are the upcoming holidays we have, and do any kind of treatment. If we need to do any kind of adjustment for holidays, after doing so, we can see this is the volumetric data looks like against each of the tasks. I show that from Excel, and the same data uploaded on Python here. So once the volumetric data is uploaded, we also upload their data by different buckets. So here we have bucket like TP1, TP2, TP3. So this is another level of complexity, is what is the priority of those activities, right? So one, I know that 333 is volume I have received, but there is a possibility that I don't have that many resource to complete the task, right? So what is the priority? So maybe priority is 104 of 333 is my top priority. Then the second priority, third priority, fourth priority, fifth priority, like that, right? So at least 104 activities of these needs to complete on that particular day itself, whereas TP2 can stay on my bucket for another 2 days or so. TP3 can stay maybe for another 3 days or something like that. So here also we have added those bucket wise distribution of those volume, right? So, and then we have uploaded the average handle time. We have seen that for each of the tasks, what is the handle time, average handle time for each of the tasks by different expertise level. 40 minutes for task 1 by analyst, 30 minutes for reviewer, like that. And then we upload the skill sets. So skill sets, we have seen all the resource And for each of the activities, whether they are analyst or they are reviewer or maybe they are DSC. NN means they don't have any skills for this particular area. Okay. So after uploading the skill metrics, we have seen in the PPT what we have done. We have converted that into a skills group. All the resource with the similar kind of skill sets, right? So here you can see that all the resource 1 to maybe 4, they have similar kind of skill sets, right? No, sorry, this is already group. So here you can see here maybe resource 1, Catherine and Mohammed has similar kind of skill sets. They both can do analysis for task 1 and task 13, right? So we'll group them into same cluster. Similarly, we'll look for other resources. Here Nandini also has the similar kind of skill sets. We'll try to find all the resource having similar kind of skill sets into same group. So here we can see each of the group has similar kind of skill sets, and we'll identify how many such resource we have for that cluster. So here we have done that, and we'll name each of these as a different group. So we have done that. So G1 means maybe group 1. Here we have 9 FT. Each FT can, each resource can work on maybe task 1 activity. For G2, all resource can work on only task 2, whereas G3, we have 2 resource who can do work on task 7, like that. And you can see here we have defined some cost. Cost is nothing but a penalty functions using maybe game theory approach. We consider who should have the higher cost. Anyone having multiple skills or maybe superior skills will have higher cost. So we'll deploy the resource with lower cost first, so that any complex activities or maybe any work coming for any of those area can be we will keep those resources as preserved, and we can deploy them whenever those are required, right? So that's how we are defining cost for each of the clusters. And you can see here the maximum cost is coming as 70, where the cost functions is defined based on their skills level and number of skills they have. So their skills level is 14 here, and the number of skills are also quite for multiple skills group, and that's why the total cost is also quite high. So we have converted that resource skills group into skills metrics, and then each we assign as cost or penalty for each of the group. And then we have each of the group, and we parallelly club their experience areas, and now we'll convert that into maybe LPP problem. But before that, we removed all the non-skills areas. So group 1, all the resource and their skills level, and these blanks are the area where they don't have any skills. So now we are sorted with the supply side. So now we need to consider the demand side. Demand is nothing but the volume metric. So we know how much volume we have received in historical periods, and we'll do the forecast for the future dates. So the forecasting can be done using multiple algorithm. Here we have used 2 algorithms. One is Prophet, another one is Sarima. So Prophet is developed by Facebook. So sometimes we get constraints not to use it. So that's why we are using with some condition whether we are going to use Prophet or not. So if we don't use Prophet, so we can use ARIMA function as well. ARIMA is ARIMA with external regressor here we have used. So what is external regressor? So here we have considered some seasonality factors like maybe number of volume is different by different months, right? So if I consider academic area, maybe during December or maybe during any festive time, there might be less student. But if I consider it for any any corporate areas, where if I consider for apparel industry, so December months will be the higher volume months, or maybe August month will be higher volume months, considering people will buy more, and that's why the volume for the apparel industry will be quite high. Similarly for e-commerce industry, where maximum purchase happens during those festive seasons, and that's why the volume for that for different backend activities will increase during that month. So considering those seasonality, we consider month as one of the factors which we can consider as regressor. Other than that, we also can consider different time periods of the year. So here I have considered we have considered last week of December to maybe first week of this January. That's the time period. Maybe either the volume gets quite high or maybe volume goes really low, right? Similarly, we can consider here I have considered last week of the year. So we can consider different time periods of the year, and we can treat them differently. Even not only different periods of year, we can consider different periods of week, months differently to consider in our prediction algorithm, so that our future prediction is also aligned with the strategy that we are taking. So here for we are preparing the regressor factors for ARIMA with some external regressors. We have considered month as regressor as well as last week of year, and then we have done the ARIMA with those regressors, and here we have created the initialized the future months, how many months we are going to do the predictions, and initialize them, and then we have done the predictions. So once we have done the predictions, so this is how the prediction looks like. Sorry. Yeah, so this is how the prediction looks like for the future days. So we had volume till maybe July 2nd, or maybe end of June, and maybe first and second maybe weekends, and that's why the third onwards we are getting the predictions for the entire volume. Once we have the volume for future days, we'll start with the start distributing that volume by different. We have considered all 1 0 wherever there is any task 7s can be done by one particular group, that's why 1, otherwise 0. And we have added a couple of additional column to consider other constant into the matrix. And here in July was weekend, and then we have all the volumetric, and that volumetric is distributed by different tasks. And once we got the forecasted volume, we got the skill sets by different groups. This is how task level groups look like, and this is how the skill matrix looks like, and this is how the schedule look like. But how to read this schedule, right? So let's try to understand for a specific days. So this is how the data looks like. Yeah. So now if I consider one specific date, this is how this days looks like. Whatever the demand I have, whether I'm able to fulfill by this, so that's what optimization algorithm is taking care of. So here what we can see here, so for task 1 we are deploying 16 resource from different groups, and at the same time we need to make sure how many resource we are deploying in total, whether that's within the number of resource or not. So we are deploying around total 70 resource from different groups. And if I consider how many resource we had, so we had around 98 resource. So out of 98 resource on a specific date, we are deploying 70 resource, right? So this is the optimal scenario, but what will happen in practical, we'll deploy all 98 resource. However, we'll maybe have less work for all the resources on that specific date. There might be on the other on the other kind of scenario where we'll have more work than the resource availability, and that time we'll create backlog for the next day or so. At the same time, what we are going to check here, for group 1 we have deployed 9 resource, and here if we see how many resource we had, for group 1 we had 9 resource, for group 2 we had 3 resource. Let's see how group 2 we have deployed only 3 resource. Group 5 we have deployed 12 resource, and if we consider group 5 we had 12 resource. Out of 12 we deployed 5 resource. So we are not going beyond how many resource we have. So optimization algorithm is able to take care of the constant that it is deploying less than the number of resource availability we had. At the same time, it is also considering the volume that we have, whether we are able to complete that or not. Okay, so with this, basically, if we come back to our presentation, so this is how we considered each of the resources, their skills, how we converted them into groups, and then we assigned penalty for each of the group, and we had the count of each of the count of resource for each of the groups, and then we converted that into a optimization problem where C transpose X was our minimization function. Here we are minimizing the costs or penalty subject to X less than equals to B, like all the allocated resource less than equals to my available resource. So here it is giving the total number of resource we are allocating and the total number of resource I have available for each of the group. So this should be less than equals to my allocated resource. At the same time, we calculated the number of resource we need for each of the tasks for each of the day, whether I'm deploying more than that resource or not. So this is satisfying that condition as well. And then the penalty is calculated based on how many resources we are deploying from each of the group multiplied by the cost functions. The cost, so here we have considered 10 is the cost for this group. So 15 into 10 is the 150 is the cost. Here you can see here the cost is high. That's why algorithm has not deployed any resource from this group, because the penalty for this group was quite high, and we are summing the total penalty and we are minimizing the penalty functions. So if we go ahead with this, so this is how this conversion looks like. All the variables are in this matrix, all the variables like where we are deploying how many resource. So all those are x till n. So since it's 8 cross 20 26, so the matrix will be 1 cross 26 into 8, because each cells represents one variable. So 26 cross 8 will be, which is 208. So will have 208 variables in this scenario. However, we had more, considering we considered more than 90 resource and more than 40 or such groups. Similarly, so this many coefficient matrix will also have this many coefficients, size of 208 cross 1, and this is my constant inequalities. Constant inequalities will have 208 cross 34 matrix. How this is being achieved? So 208 is the 208 is coming 26 into 8, because 26 in plus into 8 will be the m cross n will be 8 plus 26. How this 8 plus 26 is coming? 8 is the number of activities, and then 26 is the different groups. So we'll have that many inequalities. Because one side inequality is coming row level, one inequality is coming on the column level. So we will have 8 plus 26 inequalities. So the B matrix will also be 1 cross 34. 34 is coming 8 plus 26, and the minimization function is C transpose X. And if we run the optimization algorithm, this is how the result looks like. All how many resource from group 1 will be deployed for task 1, for task 2, and the total number should be less than equals to the availability, and also the how many resource I need for task 1, that should be less than equals to my greater than equals to my required, so which is 18. So this is how we try to solve the real world scenarios for different kinds of activities in the industry. This can be for any kind of industry, whether it's a back-end operations or maybe any construction world. And construction world can have more complex problem, considering there are some dependencies like maybe one activity can start once the previous activity is completed, right? So those kind of scenario will add additional complexity on top of what we have described in this problem statement. And so mostly all operations where we try to solve demand supply balance, we try to solve using this kind of approach, because in most of the industry is balancing demand and supply. How good we are in balancing demand and supply, that's how we are running the business in a more optical manner, and that's where we are more towards profitability, or maybe less towards the loss. And in most of the case, supply is manpower, machineries, raw materials to complete those activities. Meeting SLA is nothing but service level agreement. LPP or game theory plans plays an important role to maybe balance those demand supply to maximize profits, or maybe minimize loss. So here I try to give a very simple visuals where we have demand and supply. If we are balanced, that's where we are maybe making maximum profit or maybe minimizing loss. If we are towards the demand side is high, which means we are understaffed. If we have supply side is high, which means we are overstaffed, right? So in both the cases, we are losing. In understaffed, basically we are not able to deliver how much the demand we have in the market, so definitely we are losing opportunity. On the other side, if I have oversupply, which means we are paying for the payroll cost, or we are not able to make enough profit with the supply or maybe payroll that I have on my account. So with that, I'll take a pause. If there is any questions or anything, I think I'm end of my presentations. Abhishek sir, over to you. Any, if we can open this forum for any question answer or.
Yeah, thank you, Suman. Let's see if so anybody on in our Google Meet link can directly ask question if they have any. I will check for our YouTube link. So just one announcement. We are thankful to all the viewers and presenters and participants, because for first day's view is more than 1,000. So just now I can check. It's more than 1,070 even. So that's a great thing. I hope that today's view will also maybe cover that one also. Okay, so any question, those who are in our YouTube link, so kindly write down your questions so that I can directly convey it to Shumon. Okay, so it might be a comments or question, I'm not sure. It says that everywhere we are applying linear algebra. Yeah, that's true. Everywhere, it's not only in maths, but in different fields like data science, AI, ML, it's full of maths. That's why I think Elon Musk already mentioned about that. The students should also take care of maths and physics for basic understanding of all the things. So it's good. Okay. Maybe using simplex method. Okay, some question was up to how many variables can a problem be solved manually using the simplex method? One question that I can find it.
Okay. Manually, see, I think if it is more than two variables, that's where problem starts, right? So it can we can solve more than two variables, but more and more variables will add. It will add up to the complexity to solve manually, and that's where all those coding language with all those algorithm helps to solve those complex problems. But manually, I'm not sure how many maximum variables we can consider for manual problem solving. Maybe more than two, but I don't have the answer, like what will be the maximum size of the problem which can be solved manually. But in any coding language, we can take n number of variables. The more and more variables you will keep on adding, the runtime or the complexity of the algorithm will keep on increasing. So that's why the runtime or resource will be will require will definitely require more resource. So maybe you need a server to run very complex, or maybe where we have more number of variables.
Okay. So not many questions yet. So maybe just very few questions that are usually asked everywhere. Like your background is maths, then you shifted to data science and AI/ML domain. So how was the transition? Like, what are the difficulties that you faced when you transform from yourself from maths background into this field? So can you, if you give a brief idea about this?
Sure, sure. So, to give a quick background, how I started this journey. So, after completing my graduations on mathematics honors, I completed masters on mathematics and computing, and with that, I started gaining that interest on maybe coding language, as well as integrated maths, basically with computer science. Unfortunately, I got a job in healthcare analytics field. Initial period was really difficult because I started working on US healthcare analytics area, which was quite new for me. In data science or in analytics, other than maybe technical side, you need to understand the domain very well. And for me, healthcare domain was quite new for me. Understanding the healthcare domain was the first challenge for me, like how the US healthcare domain works. Like each and every diagnosis or maybe procedure has a procedure code or diagnosis code. That's how each and every data are being tracked. And with that, what kind of analysis can be done? I used to work on fraud, waste, abuse area. Like what kind of fraud can happen in healthcare area, right? To do so, I had to understand how the healthcare industry work first, and what kind of fraudulent activity can be done in those kind of areas, and what kind of statistical or mathematical algorithm can we build to identify the anomalies which are basically the fraudulent activities, right? So definitely it was not that easy, but it was interesting. So I learned during my job, I learned healthcare domain. I worked for around 7 years in US healthcare domain, and after that I transitioned to banking finance domain. Currently I'm working on banking and finance domain, where I learned the banking domain, how that works, and here what kind of data science or banking or analytics activities are done, and where we can contribute from mathematics. So I would say initial period may not be that easy, but it was interesting. So each and every phases I got challenges, but at the same time I learned a lot, so that it makes me interested to go one level above in each of the stages. I'm not sure whether I answered the questions or anything specific you want.
No, no, yeah, yeah. It's a very good journey, and it's really, I guess, you learn many things, and I'm sure that the learners who are going for this data science and ML will also be helpful from your experience that you had. Okay, the next question or maybe comments could be like so nowadays when I talk with my friends who are like you, where you are in a very high position in companies, when they talk about this, usually say that nowadays the students that you are getting as a employee for the first employee, like very freshers like that, then the knowledge that they should have may not match with the standard that you were expecting, because it's a very fast moving area, and people have to learn and at the same time have to unlearn things.
Yeah.
So what could be your idea that the students should, if they are thinking of going for data science as a future career, then what should learn from the very beginning so that this gap could be minimized?
Yes, I think in question itself you already answered the question itself, like how quickly a person is learn and unlearn, or how adaptive a person is. So in most of our current interview, we consider that as the key recruitment factors, how positive a resource or maybe a freshers is, even that person is not having maybe that particular skill sets that I'm looking for, whether that person is trainable or not. And to maybe prove that trainability, we see that openness. Whenever we are asking any questions, how open that person is to take that and trying to answer that questions, not just maybe bluffing, saying that I already have done that or something. So accepting that the facts that this I already have learned in my education. However, I have not learned these things, but I have the capacity where I can gain that knowledge maybe during my work, and I'm a quick learner also. So that's something we look for when we recruit from market at this moment. But if I want to say what kind of technical skills that we look mostly, the sense of data is the must things, like how good understanding each individual that individual has about data. Any coding language, it can be SQL, it can be Python or R, definitely a plus. And nowadays it's a good to have or must have at least one coding language, and preferably Python. One visualization tool, either Power BI or Tableau. Maybe few months back I would answer as maybe Tableau as the preferred, but now world is shifting towards Power BI. So maybe having knowledge on Power BI is definitely plus. So Python, Power BI, on top of the academic skills, whatever they are learning in mathematics or statistics, economics, or whatever subjects they are learning.
Okay, thank you. And nowadays, what are the new upcoming technology that one should learn about? So yesterday I was talking with Dean of IBM Research USA. He was telling that few of the blogs could be helpful for that, which will actually explain what are the upcoming technology or what could be the technology that one should learn. So can you give some more idea about this, how a student can think of for future technologies that he or she should learn?
Yeah, definitely. So I think Dean might have already given the correct answers, like different blogs will give us exposure to understand what is happening in the industry. However, on top of that, for student, I would say if they are actively participating on Kaggles, at the same time they are enrolling in different e-learning courses from maybe Coursera or different other portal for upcoming courses that are easily available on those e-learning portal, because the industry is moving really really fast, and that's why the if I say something to learn today, maybe tomorrow it is going to be old, right? So we need to learn whatever is coming up. Few months back it was maybe generative AI, now we are talking about more about agentic AI, and maybe tomorrow we'll talk about something else. So whatever is going on in industry, we should definitely keep at least basic understanding of it from different blog or maybe e-learning portal. At the same time, if we participate on some competitive portal like Kaggles, or maybe we are participating in any hackathons and all, there also we learn. For student, it is going to be a learning opportunity for them to understand what is happening in the world at this moment.
Okay, I got another question is, sir, instead of Power BI, Matplotlib will helpful or not?
Matplotlib in industry rarely being used. In academics, it's being used a lot, I know. But in industry, we are using either Power BI or Tableau. There are few in maybe corporate use ClickSense, and few other visualization tools. But Matplotlib, not sure.
Okay, so there are, I don't find any further questions. So those who are in Google Meet may unmute yourself and may directly ask questions if you have any. Okay. If there are
I
no
have a
further
question.
questions, yeah, so please. Shati Mukherjee, yeah, please.
Yes. Sir, you have used linear programming throughout. So is there any scope for applying nonlinear programming?
Yes, definitely. So depending on the problem statement, you will apply linear or nonlinear programming considering the problem statement.
Okay, and you have lots of data there, and can you use the genetic algorithm and like that?
Yes. We used, so I can give quick example. Recently we solved one complex problem for transport. So each corporate provides transport to their employees, right? So to provide transport, so they need to optimize multiple things, like we need to have the maximum occupancy in the cab. However, we need to consider that cab is not rotating throughout the cities, right? So it should have minimum deviations on the route. So whosoever is en route, those employees needs to be clubbed together. But industry does not operate in maybe 9 to 6 manners, right? Each and every hours there is a shift, right? So and I cannot maybe wait one 9 p.m. employees with and club that employee with 10 p.m. employees. So with all those complexity, we considered genetic algorithm as well to solve that problem, to optimally allocate cab for employees for their pickup and drop.
Thank you, sir.
Thank you.
Okay, so I cannot find any further questions. So now it's a time for us to thank Shumon. It was nicely done. Thank you very much. And the students are really helpful from your answers. And thank you once again, Shumon, for joining us. Okay.
Thank you. It was really my privilege to be part of this. Thank you. Thank you, everyone.
Okay. Thank you. So now we'll move on to our next technical session. And I can see that to chair this session, Professor Eric Trail is already amongst us. So may I request Eric to please take over the session? I'm sure that all the speakers might also be joining us. I can from US, so it might be too early for them to join, but they will certainly join us shortly. So it's my great pleasure to hand over the session to the session chair, Professor Eric Trail from Linköping University, Sweden. So Eric, the session is yours.
Thank you so much. Thank you. Yes, it's coming sharp on time here, and I really look forward. It looks very exciting. A lot of subjects, a lot of countries. So it's gonna be nice experience, I think. And keeping time also is very good. And I think I can already know then perhaps call Okku Gürel from Turkey. I hope the pronunciation was adequate. Anyhow, to join us and talk about new insights into generalization of Bernstein operators. Please, welcome.
Yeah. Welcome. Thank you. Thank you so much. Thank you for your introduction. It's a great pleasure for me to attend this conference. Okay, now I will read my presentation. Okay, it's okay. Is there any problem, as you see? Okay. I think there is no problem about my presentation.
Yeah, we can see it clearly. Yeah.
Okay,
Please go ahead.
Okay, thank you. Okay, again, thank you so much for your introduction. I am Övgü Gürel from Recep Tayyip Erdoğan University, Turkey. And today I would like to present my work titled New Insights into Generalization of Q-Bernstein Operators. And here is the outline of my presentation. I will begin with the basic background, including approximation theory, the Weierstrass theorem, and Bernstein and Stank operators. And after that, we will introduce the quantum analysis and the Q generalization of Bernstein and Stank operators. And we will focus on a new representation of Q-Stanko, and we will discuss some practical Q generalization of these Bernstein operators. And at first, the Pasch work was not widely known because it was published as a local conference paper. So in subsequent years, interest in Lippasch construction grew, and the number of further studies were also carried out on this topic. And here is the definition of Lippasch type Q-Bernstein operators. And also, 10 years later, in 1997, Phillips developed another form of this operator. Here is the Phillips Q-Bernstein operator. And this operator is particularly useful due to its polynomial form. So we can say that when Q equals 1, both Lippasch and Phillips version turn into the classical Bernstein operator. And in addition, when Q is not equal 1, Lippasch version produces a rational function, while Phillips version gives us a polynomial. So Phillips version is more useful than the Lippasch version. And also, when Q is between 0 and 1, both operators are linear and positive, but when Q is bigger than 1, so Lippasch generalization still keep its positivity, while the Q-Bernstein operators have not this property. So it enables us to research this operator when Q is 0 and 1, when Q is bigger than 1. So it is important for our research. And also, I want to give some theorem about this operator. In 2003, Ostrovska proved that the moments of this Q-Bernstein operator are related recursively. And also, after Ostrovska's recurrence formula, another relation for the Q-Bernstein operator was obtained by Widenski in 2005. So another problem is what happens as the degree n tends to infinity for the operator. In this limiting case, the researchers obtained the so-called limit Q-Bernstein operator introduced by Insky and Ostrovska. We can see that this operator can be expressed in terms of an infinite series involving the node 1 minus q to the power of k. And also, the next theorem was proved by Ostrovska and shows that the sequence of Q-Bernstein operators converges uniform to the limit form on closed interval 0, 1. So in other words, we can say that as n goes to infinity, the finite degree operators approximate the limit operators arbitrarily. And with this uniform convergence in hand, we can now present an other recurrence relation satisfied by the limit Q-Bernstein operator. And while Q-Bernstein operators are powerful in maths, they are special cases of a more general family. Introducing the parameter alpha leads us to the Q-Stank operator. So we talk about the classical Stank operators, so we can generalize it, the Q-Stank operator using the parameter Q. So which generalized Q-Bernstein operator in the Q framework. And this operator constructed by Novak in 2009. Here is the definition of Q-Stank operators. These operators generalize several well-known operators for alpha equals 0. They coincide with the Q-Bernstein introduced by Phillips. For Q equals 1, we can reach the classical form, this operator. And also for Q equals 1 and alpha equals 0, they further reduce to the classical Bernstein polynomials. Now, we have reached the main part of our work. Although Novak originally defined the Q-Stank operator, we have derived a new representation of this using the Q-Pohember symbol. Using the Q-Pohember symbol, we provide an alternative expression for the coefficients in Novak's definition as shown in the following lemma. So we can write the basis polynomial of this operator in terms of the Q-Pohember symbol. And using this representation, the Q-Stank operator can be equivalently expressed as follows. And as you can see, the coefficients are arranged in terms of the Q-Pohember symbol. And now we turn to moments of this operator. So these moments were previously established by Novak. However, we provide a different proof technique. Why Novak used the representation of the operator in terms of the Q difference? We calculated the moments using sum involving the Q-Pohember symbol, such as Rota theorem and Stanko theorem. So we can say that also moments reduce to the special cases of the well-known operators, as you see. Now, we present the recurrence relation satisfied by these operators. In particular, we applied technique used by Ostrowska, which she proved using the definition of the operator and some calculations. We simplified this recurrence relation, and also using the other relation for the basis polynomial for Q-Stanko, we can also derive another relation as shown. So why important this operator, these relations? Because these formulas will allow us to compute the explicit moments of the operator. So we can calculate all moments of the operator, and it helps us to get the information about the approximation theory and also degree of the approximation. And also, as we previously discussed, so we can say the moments of the operator can be derived by evaluating the recurrence relation at specific values of m. And in addition, by setting alpha is 0 in the first and the second relation, we recovers the relation previously obtained by Ostrowski and Widensky respectively. And also, in studies on Bernstein type Q operators, the limit form of these operators play a key role. Until now, the limit of the Q-Stank operator introduced by Novak couldn't be obtained. The main difficulty comes from the infinite products in the basis polynomials which diverge as n increases. And in the previous section, we rewrite the basis polynomials and it's in the form of Q-Pohember symbol, where these products become convergent. So this transformation makes it possible to define the limit Q-Stank operator. And now, before constructing this limit operator, we present some auxiliary results that we will need in the next steps. Here we prove for each k, the basis polynomial p and k for the Q-Stank operators converge uniformly on the closed interval 0, 1. And the other lemma prepares the ground for defining the limit operator. It should be noted that this convergence holds only on closed subintervals of 0, 1. So in particular, this series diverges at x equals 1. So if x equals 1 is a problem, we have the next lemma, because since the coefficients P infinity K, I want to say yes, constructed from products of non-negative Q-Poember factors. So each coefficient is non-negative because of the Q-Poember factors, and also the summation of P infinity Q equals 1. And another lemma plays a key role in establishing that the limit operator acts correctly on continuous function on 0, 1, because in the previous slide we see that x equals 1 is a problem for the convergence of the series. So we have to define this operator when x equals 1. So if using this lemma, we combining this uniform convergence of the basis polynomials, the positivity and the normalization properties and the continuity at x equals 1, we can now introduce the limit form of this operator as well. So we write, okay, this is a limit Q stank operators, but also we don't know when n goes to infinity the SNQ, the classical Q stank operators converge as infinity or not. We don't know. So the next theorem allows us to coincide that the limits of sequence of Q stank polynomials is the operator as infinity, which we called limit Q stank operator. Now we can say yes, this is the limit of SNQ. So at this point we present the first 3 moments of this operator, which follows directly from the definition, but to find the general form of general expression of the moments is important in our research. However, if we wish to obtain the general form of this moment, so this will be established in the next theorem. And finally, we think that if Q stank operators have recurrence relation, and also the Q-Bernstein, if we went to the past, Q-Bernstein operators have the recurrence relation. What if the limit Q stank operator have this property or not? And finally, I would like to present 2 recurrence relations satisfied by the limit operator. And taking alpha equals 0, the derived recurrence formula coincides with the relations satisfied by the limit Q-Bernstein operators. So the complete list of my references for this presentation is given here: Bernstein, Insky and Ostrovsky, Lipash, Novak.
Well, thank you very much. Thank you for this. Very interesting. And it seems that there are big potentials for developing various functions here, which is so fascinating in this sphere. And I think you made it excellently. And of course, wonder if there are any questions. If so, just ask. So there seem to be no questions. So you made also a very clear presentation here, and then we can move within time to.
Thank you so much.
Yes, very good. Yes, and very clearly presented also. And we have come to the next presentation, which is from Romania. That's exciting. And it's Gabriela Apretuese. And the title is The Dual Characterization of Approximation Elements with Respect to a Closed Convex Non-Void. Yes, that is exciting too. So please take the chair and start if you're here.
Thank you very much for this introduction. Here is the main problem. Consider X a linear normed space. We denote here the closed ball of center X and non-negative radius D. Closed balls in dual space X star. Here is a distance from X to a non-void convex set C, given by this infimum. And here is inequality about the C. In this talk, we study basic properties of the multivariate mapping given by dCxD, where C is from X, D is non-negative, and dCx and D is a set of all elements from dual with norm D, and which verify this inequality for all V in ball of center D and the radius D, and U from C. Using this mapping, naturally generated by the geometric problem of separation of non-void convex closed sets and the closed ball, we give connection with some important concepts and properties of convex analysis. Epsilon subdifferential of distance function, epsilon approximation element, duality mapping, polar cone. So this multifunction become a tool, an interesting tool to investigate convexity problems. Here are some notations and definitions. An element Z from C is an epsilon approximation of X in C if we have this inequality. If epsilon is 0, we obtain the best approximation of X in C. If epsilon is positive, then the set of epsilon approximations of C is always non-void, but the set of best approximations can be void. We denote by PCX the set of all best approximations of X in C. This is a metric projection associated to the set C. If PCX is non-void for any X from X, the set is called proximal. And if PC is void set for any X which is not in C, the set C is called anti-proximal. Here is a definition of epsilon subdifferential for an extended, real extended function. The definition of the domain of F, a definition for a proper function, and in the case of epsilon 0, we obtain the definition of a subdifferential of the function f in X. And also here is a type of multivalue operator epsilon monotone. But there exist other types of monotonicity, and also the definition for duality mapping. And Here we present Garkavit theorem. If X is not in C using separating hyperplanes, Garkavit has obtained a dual characterization of a best approximation elements of X in C. If C is non-void closed convex set of a linear node space, an element Z is a best approximation element for X if and only if there exists an element for dual x0 star such that the norm of x0 star is this norm, and also we have this inequality for all U in C. A simple remark. It is easy to prove that the second condition, the second conclusion of Garkavit's theorem can be rewritten by these two properties. We have here the value of x0 star in X minus Z, and of course, if 0 star of Z is a supremum of this set. This suggests us to consider the following set, the set of all elements from dual of norm D, and also we have this inequality for all V from ball of center X and radius D and all U in C. Geometrically, for each X in X and positive D, DCXD coincide with a set of all linear continuous functionals X star with norm D, and the hyperplane X star I is equal by a constant K is a separating hyperplane in between the set C and the ball for certain constant. In the spatial case D equal DCX, we denote DCX this set, and we consider the situation with interval 0D. And we obtain two generalizations of Garkavit's theorem, light generalization. We investigate this multifunction, and for this, our first step is to establish a dual characterization of real non-negative number D, such that D is less or equal than DCX. So, let C be a non-void closed convex set in a linear node space X. If X is a fixed element in X, then D is in this interval if and only if there exists an element from dual such that the norm is D, and we have also this inequality for all U in C. So, here is a proof. I omit it. If we denote A, the elements from dual with the norm D, and which is verify this inequality for all U in C, if D is in this interval, then A is in DCXD, and if D is 0, DCX is 0 also like as A. So we can rewrite DCX and D by these two conditions. where D is in this interval. So this theorem is a light extension of a characterization established by Barkavi concerning the best approximation elements. Another generalization is given by the following theorem. Consider X a linear North space, C a non-void closed convex set of X, epsilon in this interval, Z epsilon is an epsilon approximation element for X which is not in C, if and only if there exists an element of dual such that the properties, the two properties of the above theorem are fulfilled from D equal with this expression. In fact, the set DCXD is generated by the problem of epsilon approximation. If epsilon is 0, we obtain Garkavi's theorem. Now we intend to characterize the elements of DCXD using the epsilon subdifferential of DCX. And we obtain first these two inequality for all elements in epsilon subdifferential of DCX. And we recall the definitions for polar set and conic polar because we need them in the following theorem. Consider X a real norm space, X from X, C a non-void closed convex set. And we have some situations we describe in three of these properties the epsilon subdifferential, the elements of epsilon subdifferential of DCX. And in the first property, we have described the elements of DCX and D. Here is a boundary of ball of center 0 on the radius 1 in dual. We have this situation if 0 is in C, X is not in C, and epsilon is greater than DCX, we have this formula for epsilon subdifferential of DCX. If 0 is in C, X is not in C, and epsilon is DCX, we have another formula given by X minus C plus. And if X is from C, then the epsilon subdifferential of DCX is given by this intersection for every epsilon, positive epsilon. In the special case D is DCX, this situation is considered by Ioffi and also by Penot and Rasmihalo. Hiriat Urruti has obtained a general formula for epsilon subdifferential for a marginal function. Particularly, we can obtain the formulas for epsilon subdifferential of distance function, which is considered either as a marginal function or as a convolution of the norm of the indicator function of the set C. But by theorem above, we'll establish some explicit properties of epsilon subdifferential of DCX. The fourth assertion of the above theorem has obtained by Hiriat Urruti. Also, we have this equality. In the case in which C is formed only by 0, we have the following two equality. Here is ND such that norm of x minus d is positive. Here is norm of x. And the result about wake star compactness, if C is a non-void closed convex set in X, then then D is in this interval. The set DCX 0D is wake star compact convex set in dual. Particularly, it contains extreme elements. Now, a property of the mapping DCX DC can be equivalent defined using a min-max property. The function fx x star u is convex concave, and using a min-max result, we obtain this inequality. Here, the max means the supremum is attained. Also, x is in DCX if and only if x star is a solution of max-inf above problem. So we have this equality for DCX. Also, if C is a proximal set, then there exists a section CC, SC, such that the identity operator can be written like as a sum between PC and SC. And finally, monotonicity property for this multifunction. We obtain this property. Here we have epsilon 1 d1 minus epsilon 2 d2, where epsilon I is given by this differential for all xi star from DCX and D. Here are some references. This talk is based for the first two papers. Also, here is the paper of Garkavi. Thank you for your attention.
Oh, thank you very much for this nice talk. And again, keeping time and keeping a very clear presentation. And must be questions here. So please, are there any questions? So present them here. Well, there seem to be no questions about this. So then I thank you very much. And I then call next speaker, which is my dear friend Carl Slopes, who I met at the very first meeting here so many years ago.
Yes,
And
always
welcome,
a pleasure.
welcome.
Let me get my presentation up and
Yes, you are presenting now. Yes.
Okay. Okay, I'm ready to go.
Yes. Welcome again. Welcome.
Okay, thank you. I'll get started. Spatial space is the venue where something or nothing happens in space. Per this research, the venue potential comes from the 4D spatial space subspace within the crystalline balanced system of system multi-dimensional fabric of space. There are three subspaces within the crystalline MD fabric of space, which is spatial space, temporal space, and EM space.
Well, just a minute. So, are you presenting something? We are unable to see your screen. Yeah, now it's fine.
Now I got to find my presentation.
Okay.
You see it?
Yeah.
Yes.
Okay, sorry about that.
Yeah.
Okay, I'll continue. The subspaces have unique potentials and characteristics that manifest in crystalline curved MD fabric of space due to the presence of mass and/or energy. Subspace components are curvature, charge, vibration, and the subspace specific primary tone. Primary tones are the fourth dimension. Subspaces are modeled as the base of a Sierpinski tetrahedron with the MD fabric of space tetrahedron on top. In crystalline flat MD fabric of space, potentials balance to a relative zero. In crystalline curved MD fabric of space, potentials are realized and rebalanced to a relative zero that is above or below crystalline flat MD fabric of space. The concept of 4D spatial space or a subspace implies interactions between the other subspaces, which are the temporal space and EM space, in the construction of the crystalline balanced system of systems, curved or flat MD fabric of space, plus its interfaces. The crystalline MD fabric of space is seen as a medium having 23 degrees of freedom plus its interfaces. Space-time has 3 degrees of freedom plus its interfaces. The concept of subspaces allow the crystalline MD fabric of space to be a separate entity from the objects and or events within the crystalline MD fabric of space. If spatial space within the crystalline balanced system of systems MD fabric space is a sustainable theory, then space, fabric of space, space-time, etc., has more characteristics than 3 dimensions of space and 1 dimension of time. What we see or experience is not all there is to 4D spatial space or the crystalline balanced system of systems MD fabric of space, a medium or venue. Right now, 3D fabric of space, it represents a vacuum. And we now are talking about gravitational waves and, you know, how, well, I won't go there. I'll get too deep. In this research, spatial space is a characteristic, a subspace of the crystalline balanced system of systems, multidimensional fabric space. The 3 subspaces of the fabric of space is spatial space, temporal space, and electromagnetic space. And that's what I've been demonstrating so that I can demonstrate that they balance to zero. But first, I'm having to go through and having to define what I'm talking about. And so in this talk, I'm trying to define what spatial space is. The subspaces are potentials that interact with each other in the mass E equals mc squared, but they are separate entities from each other. So the fabric of space and the things that are in the fabric of space are separate entities. So we have those potential interactions, and what I'm trying to drive out is that we don't look at space as just being space and it's just one thing, that there's structure there. By assuming that crystalline MD fabric of space is a separate entity from the mass that's within it, allows the questioning of how they work individually in or at points where they interface with each other. Does the universe recycle itself? Does it recycle mass and the events that are within it? From the Big Bang to the current state of the universe, could the universe be seen as having increase in chaos or in order? If there has been an increase in chaos, then that could be equated to a loss of information. If there has been an increase in order, then that could be equated to an increase in information. This information could be the patterns that drive, design, and or support the existence of the crystalline MD fabric of space. Mass and energy down to the subatomic particles. Most of the volume occupied by a single atom is empty space. Per this research, the empty space is crystalline MD fabric of space at an atomic level. In considering the composition and characteristics of the atom, is there a need to consider the interaction between subatomic particles in the crystalline MD fabric of space? In addition to the mass, is there a need to consider the source of energy, information, patterns, and medium that drive, design, and or support the existence of an atom? At an Earth equals 1 curved 4D spatial space is balanced to zero or balanced to zero by curved 4D temporal space and curved 4D EM space within crystalline curved MD fabric. I shorten this actually later on to just being ether. But the concept applies that the crystalline curved MD fabric of space as a medium could be flattened by opposite values of 4D temporal space and 4D EM space. The concept is supported by the color pattern as expressed by the 10x circular constants that's identified here. All 10x circular constants must use a long second time base, which is to argue that gravity is a potential within the medium of crystalline curved MD fabric of space versus it being a theoretical particle or graviton. So this is just me showing how I determine temporal slope instead of using curvature as Einstein has used. The relationship exists between space and time, or a relationship exists between space and time. Einstein has already identified that, but my approach to time is that time is a spectrum instead of a single point. And that single point for us is clock time T is what I call it. And that's based on 1 second. And is 1 second universal, or is time more of a spectrum? As you approach flat space, as you're approaching the speed of light, time slows down. And 1 second doesn't explain that. As you approach a black hole, according to my temporal spectrum, time speeds up. According to general relativity, time goes to zero at the edge of a black hole. The term gets away from me, not the event horizon. So what is valid, and trying to come up with a valid model for color is what I'm trying, not just for color, but for time, and in a different approach to cosmology, and to be able to identify a temporal reference within the visible light spectrum, so that when we do look out into space, that we have a time reference that we can apply to that. And so part of what I'm doing, I'm looking at time dilation in regards to what Einstein has said and talk about in general relativity. We have contemporary versions of time dilation dealing with the Doppler effect and the stretching of the fabric of space. And if space is a vacuum, that it's making me a little crazy thinking about, okay, we're stretching an open vacuum, and how do we do that? Or we're compressing a open vacuum, and I'm thinking, how do we do that? But the answer comes back in that it's the Doppler effect. And I'm saying, okay, I don't get it. We have gravitational time dilation, and I'm asking my question, okay, we can't explain gravity. We had equations for gravity, Newton's and Einstein's, but we don't know what gravity is. And now we're adding an additional characteristic to it, in that it's related to time dilation. And so anyway, I'm coming up with my own theories about it, and it's based on my version of temporal space in time dilation. The Big Bang, just real quick on the Big Bang. If the Big Bang happened at the speed of light, and at the speed of light is zero, then time is zero, speed is zero, and energy is zero. Kinetic energy is zero. And so I'm still trying to work through that in terms of, do we have this insane amount of energy that was released at the time of the Big Bang, or did nothing happen? So this is just some other models, and I'm working through orbital mechanics and looking at sonification. We take pictures of outer space and convert them to music, and what I hear is music. And if the Big Bang is the beginning of everything, that everything from the Big Bang is going to be chaos due to entropy, the increase in randomness. And I'm thinking, wouldn't that result in static instead of music? And what I hear from sonification is music, and it's incredible. I'm also asking the question about what is powering the universe, and we need a model that would help us identify how the universe is powered. Where do things plug in? Where does the energy for an atom to be an atom come from? And we get a vacuum. We have things pulling energy from open space. So what's going on? And I'm thinking that, okay, we may have a system where things are balancing to zero. Is there a direct relationship between energy and frequency? And so with my modeling, that I'm using sound, I'm identifying color and identifying correlations between the two, and using Planck's equation, that energy equals Planck's constant times frequency. So if the fabric of space is a medium, a crystalline medium, then deforming that medium would produce a charge, and that charge would cause the crystalline medium to vibrate, and you have an energy source. So the other real quick, does the piezoelectric effect in Coulomb's law apply to the universe? So what Coulomb's law is that opposite charges attract and like charges repel. And if you have a mass or a universe moving through a crystalline structure or material, does it create a charge as it's moving through? And if the fabric of space itself has a charge, would that result in something being repelled? Since the galaxy would be the smaller item, would it see the greatest amount of displacement? And if the fabric of space and the things within it are separate from one another, would that tie in with Hubble's constant? So right now, compared to Hubble's constant in the cosmic microwave background, there's the Hubble tension, I believe, that is called, whereas the numbers of that they come up with for the expansion of the universe don't match with one another. But if you have two different systems, does it matter? You know, one is doing its thing and the other is doing its thing. These are some questions that I, am focusing on in regards to spatial space and trying to come up with a combined system and just playing with numbers and looking at E equals MC squared. If you talk about something traveling at the speed of light, that at the speed of light is 0, then if you put in 0 here, this equation just blows up in a sense, or it just doesn't do anything. Or if mass is 0, what do you do in space, or if there's no mass in that location, is basically what I'm looking at. And I played around with Newton's 3 laws, and including a crystal in the expression, just to see just what would happen, or what could happen. And this is a structure that I'm working on and talking about spatial space, temporal space, EM space, and coming up with a structure that I'm trying to identify and make work in terms of a way of explaining the cosmos somewhat. So just in conclusion, just want to say that the concept of spatial space is not the same as the crystalline MD fabric of space, because spatial space within my modeling is a potential, it's a subspace, and that the primary tones are treated, are identified as keys, and that they, identify what frequency that these subspaces are in, and each subspace has its own unique primary tone, and that a chord is a combination of 3 or more notes played simultaneously. And therefore, with these 3 subspaces, which make up the crystalline MD fabric of space, you get this structure. So that's it. Thank you.
Eric, Eric,
Thank you so much. Yes, yes, and I thank you so much for this presentation. And as usual, so exciting and an area of great speculation, but also order. And I think there must be questions now for this presentation. And please come with some.
okay, I can see one question in the YouTube channel.
Okay.
Perception shape, the fundamental models of color theory, music theory, spatial space, and what breaks first when we move beyond human created frameworks. Is the question clear to Carl, or shall I repeat once again?
Was that question for me, or?
Yeah, it's a question for you.
And it's what breaks first?
Now, again, I'm repeating. How do limitations of human perception shape the fundamental models in color theory, music theory, and spatial theory, and what breaks first when we move beyond the human created framework?
Wow. I don't know. And with starting with that, I think what I'm trying to do with my research may be to provide an answer to that question, because where do our theories come from, or beliefs come from? And we say it's not there. Is that true?
Okay. Okay, I think that might be the answer for this person who asked this question. I do not find any further questions. So
I probably scared them off.
Well,
yeah,
I think I can connect with that a bit. What do you think about the time and entanglement? Because there seem to be various areas of your diagram that do interconnect in some way, and perhaps one could solve that your way by a kind of theoretical analysis of the entanglement aspects of this. Did you hear?
Yes, I heard. I'm trying to come up with a answer, and I'm back to I don't know. If what I'm proposing is sustainable, that it could allow an understanding of entanglement, because one of the driving motivations for my research, it's an impossible thing to reach, which is teleportation. And so entanglement happens or works like teleportation. How does things that could be separated by billions of light years become entangled and respond to one another as if there was no distance between them? And if I can identify the mechanics of the cosmos, in a sense, and find a way for time to go to zero, then distance goes to zero. And that would tie in with entanglement, or could be akin to entanglement, or provide some kind of understanding as to what's going on. But still, the research is very, very young. This is from last year to now. And so this is just where I've got, as far as I've gotten with the research.
Yeah, because exciting thing about entanglement, among others, is that it is zero time.
Yes.
There is no time lag,
Yes.
and
And that's
that makes it, yes,
fascinating. But that's also teleportation. So,
yes,
and if we're
yeah,
going to
that's true.
explore space, we're not going to do it with rockets. We're going to need to be able to
Yes.
teleport.
Yes. Well, it's very exciting. It opens vistas here that one feels have solutions, and you are on it, really. And yeah, are there any other questions?
No, there are no other questions on the YouTube.
Yes.
Okay.
But then it's, I thank you, Carl. This is so exciting, and you are close to so much here, and already in thinking that that makes a difference. And now it comes here a section which interests me also, and that is the medical sector, of course. I said yesterday that it's becoming an increasing area of informatics and artificial intelligence, and it seems that we here have the tailor-made speech on that, which I look forward very much to listen to, and that is Surya Sengupta from USA, who will be talking about precisely that, understanding task utility of medical images in the era of AE and information theory. This is so exciting, so please enter the screen stage.
Can you hear me?
Yes,
Okay. And can you see my screen?
yes.
Okay. Okay. So thank you so much for the introduction and for the invite to present my work on understanding task utility of biomedical images in the era of AI and information theory perspective. So I'm a PhD candidate in University of Illinois at Urbana-Champaign. So let's get started. So I guess everyone knows about AI. People are talking about AI. There are different parts. AI is making headlines, starting from chat GPT type models to different vision models where AI are generating different images. And there are many different sectors where different researchers have been doing very cool works about how to use AI to solve more complex problem which was probably not solved in that easy way before. And one of the domains which I'm interested in is how exactly we can incorporate AI into biology and medicine. Now, definitely biology and medicine is a very diverse set of area where there are different subfields. Let's say if we focus on the more biology side of it, there are like drug discovery and all which are of interest for the industries, and then there are very basic research like understanding different genes and how to use AI in computational biology. And if you move to the medical side, there are medical imaging. There are some approaches about how to use AI in precision medicine, which means that in some cases the diagnosis needs to be tailor made with a very high precision to particular patient. There is a whole area of using AI and robotics in surgery. Lots of hospitals and clinics are currently doing this. And also there are many different clinical chatbots which are currently being developed for supporting to the patients real time 24/7 with the help of AI. So in biology and medicine also, as you can see, there are many different areas where AI has been getting very popular. Now, if we focus on, for this talk, we would like to focus on some specific biology applications. So so when I say about biology applications, there are many different ways of how we can think about it. And one way is, let's say, we want to study different cells and tissues under microscope. And what typically is currently being performed is, let's say there is a sample on a glass slide. Now there is something called staining in between, which means that we want to see a specific location, or we want to see a specific structures of the cells and the tissues. So that needs to be stained with some chemical dyes or some kind of external agents to make that particular part stand out compared to the other parts. And once the staining is done, once we know that the staining is done properly, and then the sample is put in a microscope and the imaging happens. And then you get very cool looking images. It can be images of different cells. It can be images of different tissues. Let's say you want to study how a drug behaves on a cell line, or maybe you want to see how a particular tissue looks like for different abnormalities. Or let's say we want to compare between how a tissue looks like when there is a normal condition versus when there is some disease condition. So things like that, there's a very typical way of looking at biological samples. And the staining is a very key step in routinely used in different clinics or different basic biology research lab, which works on understanding the morphology, understanding the microenvironment of different tissues of human body or animal body. Now, coming back to the discussion about like staining. So one of the important staining technique is called fluorescence. This is a kind of dye that stands out when you put things under microscope and generates a very good contrast. Now the thing is, fluorescence has been used routinely in different biology or clinical research, in clinics, in drug discovery applications. But the problem is, when you do the fluorescence, it has some effects of phototoxicity and photobleaching, which means that since you are putting a chemical dye on the samples, on the biological sample, it can hurt the health, or it can hurt the health of the sample. It can make it degraded. It can have some effects on this, which is not good for the cells to survive in different scenarios. Now there is an alternative way of looking at cells, which is called label-free microscopy, which is a parallel way of looking at cells and how exactly you can treat cells without staining. So the good thing about the label-free microscopy is you do not have to stain it, so which means that there is no effect of toxicity, there is no effect of bleaching. But also the downside of it is, since you are not using any specific chemical dye, you are not using specific fluorophores or any other outside agents, you are not getting very high molecular specificity, which means it's sometimes it can get hard to understand the different structural morphological details between different parts of the cells. Now, recently there have been some works of addressing this problem of not having molecular specificity, which is typically called virtual staining. Now what is virtual staining? So in some easy words, it's basically an AI model that takes a label-free image which did not have the staining, and then it generates a virtually stained one, which means it's a computationally generated stained images. So I guess we can think of, in a very similar line, there have been some applications on mobile where if you put your image of your young age, it tries to generate something, the image of your old age. Or let's say there are some apps where if you put the black and white image, it can generate the colored version of it. So in terms of the AI methods, this is kind of similar way of looking at it. Is like you have an AI model, you train it to generate a computational or virtual stained one by giving label-free image as your input. Now, so far so good. There are many works, there are a couple of companies that have been working on this too. But the question is, how do you understand, like, if your virtually stained images is good enough? Like, what are the ways of understanding the quality of the images, which is very important when we talk about different biology or healthcare applications. So before I talk about a little bit more details, let's maybe think about what we mean by image quality, like what exactly what exactly the meaning. So there are some metrics, as all of you can understand, that the image is a collection of pixels, like all of the images, whatever you see on our phones, on our computers, on wherever there is any digital image, it's basically a pixel. That's what a computer understands. Now, there are many metrics which are based on those pixel level details. One is structural similarity index. Then there is signal to noise ratio, which is very common in other applications too. But the problem is there are many different applications or many different scenarios where it has been seen that those measures can be misleading. If you look at the left figure, you see like in the leftmost there is an image of a nature, and then you put a very small Gaussian noise. The structural similarity drops to 0.73. But then if you change it a lot, like for example, let's say you change the saturation, you change the hue, and then if you change the brightness, the images look very different, but the SSIM is still high. So you can see like those measures can be misleading in some cases. So when it comes to medical imaging, a very important key point here is, unlike images wherever we click on phones or wherever we click out the digital cameras, unlike those, medical images or biological images are typically accurate to solve some task. It's not just there for us to say, oh, this looks good. So biology or medicine images are not just accurate to looking at it. It is accurate to solve some downstream task, to solve some clinical task or biological discovery. So it's very important we think image quality in a different way when it comes to biology and medicine, which we call task-based assessment. Okay, so we'll talk about more details about what I mean by task-based assessment. So which essentially means that when you acquire an image, you have to make sure that the images are doing a good job to solve the task you have acquired the images for. Now, let's talk about the specific applications here, or specific case studies here, where we will understand that how these task-based assessment can work and what are some of the interesting insights the task-based assessment can produce. So let me summarize the slide here. So what we are trying to do here is we have a setup of collecting label-free images, as I talked about in my couple of slides back. And then I talked about virtual staining, which means we want to generate a computational staining from the label-free images using AI. So you can think of this pix-to-pix HD that you can see in both of our figures. So this is a traditional AI model to do something similar. So where you give one image as input and you get another image as output. So we use a specific cell lines, we use the drug treatments and all. There is a specific imaging system that you use to collect the images for. And as I mentioned in a virtual staining definition, that we are using label-free image as our input, and we're trying to generate a computational fluorescence images. Now, there are two tasks that we are trying to solve. The first is we are trying to classify between the state of the cells, which means that if the cells is in control state or if the cells is in drug-treated state. So that's what we are trying to classify after with those images. The second task is segmentation, which means that it essentially means cropping, but in automated way, not manual way. So we want to study the nuclei of the cell specifically. So we want to segment those out, crop those out so that we can study the shapes, we can study the size of it, we can study the other morphological details of the cell nuclei. So just to summarize, there are two tasks which you are interested to see how the images behave on those two tasks. So one is classification of the state of the cell, like if it's in the control state, or if this is the cell which are treated with the drugs. The second is we call segmentation task, which means we are trying to crop out the nuclei of the cell from the images. Okay. So before I talk about more about the details of how the task performance goes for this particular example, let's look at some very interesting, like the just visual results of how this virtual staining works. If you look at the left figure, the first column is saying label-free QPI patch, which means this is the label-free image. And the second column is a virtually stained one, which we have generated using AI. So this is a fake fluorescence. This is not an actual fluorescence. This has been generated using AI methods. And the third one is actually ground truth. So this is the actual one which came out from the experiment. Same with the right-hand side figure. The first column is just a crop cell nuclei from label free. Then second column is a virtually stained one, and the third column is the ground truth. And there is a matrix here, PSNR, SSIM, which shows a pretty high number. So if you just like compare the general numbers of what typically comes out from those PSNR, SSIM, in both the cases the number seems to be pretty high. And if we just rely on these matrix, like the pixel level matrix, statistical matrix, it says that the method did a good job. Okay, so now coming back to the task utility or task assessment of those images. So this is the way we are trying to look at about the task. So what we are going to do is the two tasks I talked about, the classification and the segmentation. So we'll perform both the tasks separately using three different modalities of images. So one is a label-free, then the virtually stained, then the ground truth fluorescence. So we have access to all three of the modalities of the data. So we have the label-free, which we trained our AI system. Then we have the ground truth fluorescence, where imaging was actually used using fluorescence. And then we have the virtually stained ones. And we'll be doing with a wide variety of task network. Now, when I say wide variety, I basically mean the task networks, which are also deep learning models here, using different capacity. Now, not moving into the very details of what I mean by task capacity, but in general, we can think about when we use a deep learning network, when we use an AI model, there is something called trainable parameters. So these are the computational model, which is parameterized using a lots of parameters. And the more the number of parameters are, we can think about that the capacity is going high. So if you have a very small network, the capacity of the small network to solve a task is less. And then if you have a very big network and if you have a very large amount of data, then the capacity of solving a task becomes higher. On a very similar direction, there is another alternative way of looking at it is learnable capacity, which means that if you have a very big network, then the more data you give to the network, up to a certain stage, your learnable capacity will increase. So these two are the key terms which we'll be using in a subsequent analysis, like one is capacity, one is learnable capacity. So when you have an AI model to solve a task, those two things vary a lot and matter a lot. And based on that, we can design a assessment technology about how to understand the task utility. The virtual staining, the performance with the virtually stained images is actually higher than the label free. But more you increase the capacity of the model, the differences between the virtually stained one and the fluorescence and the label free, those two become smaller and smaller. And finally, when you have the highest capacity model, the label free perform exactly same like virtual staining. Now, if you move to the top right figure, which is again y-axis as the dice score, and the x-axis as the number of data set, number of training set, which again corresponds to the trainable learnable capacity of the model. So if you look at this, you find similar kinds of conclusion where when the number of images were small to train the network, the virtual staining had a clear benefit compared to the label-free, but the more data you provide, the label-free images perform as similar as virtually stained. More interesting observation can be found in the row below, which is the results for the classification task. So here the classification was between if the cell is in a drug state or if a cell is in a control state. So here the interesting observation, if you and the basic structure remains same. The y-axis is AUC, which is area under the curve, or a well-known metric to understand how good your classifier worked, how good your AI classifier worked. So when, and the x-axis is basically the models with increasing capacity. So here it shows that when the model had lower capacity, like CNN1, CNN3, the label-free images perform poorly compared to the virtually stained. But the more you increase the capacity of the model, the label-free images actually surpassed the virtually stained one. So it actually outperformed the virtually stained one, where the virtually stained was generated using an AI method. Now, if you go to the bottom right of it, like a very similar conclusion, where the y-axis is AUC of the classification performance, and the x-axis is the increasing learnable capacity. Here also, for a smaller learnable capacity, the label-free images had lesser performance compared to the virtually stained ones. But the more you increase the learnable capacity, the performance, the label-free ones outperform the virtually stained ones. So the key takeaway point from all these results are that, like here we talked about virtual staining, which is an AI method. So the task utility of AI generated images or the virtually stained images, that very, very fundamentally depends on how exactly the downstream task is solved. So whenever we use an AI method, wherever we use an AI-based processing, especially when it comes to medicine and biology, there are lots and lots of works have been going on, applying AI in different kinds of processing, generating data, making things look better and all. Now, when it comes to medicine, when it comes to biology, since we are very always interested in solving some downstream task with those AI generated images, evaluating based on the task is very important before we deploy something in real world. Now the previous results, why this is cool or why this is beautiful, because this is not something random, or this is not something specific to this particular imaging modality or particular AI methods and all. This is fundamentally rooted to information theory. So there is a very fundamental and widely known data inequality, which is called data processing inequality, that says that if you have a data and if you have some task associated with that, whatever processing you might do on the actual raw data, there is absolutely no way you can increase the mutual information between that data and the task level, which is also kind of intuitive, that if you have a data and if you have some task level associated with that, irrespective of any processing you might do on the data, irrespective of any computation you do with the data, the fundamental information content is not changing. So if you think about the results I showed in the last slide, this is what's going on those data itself. So there are a spectrum of different task network which you are using. So when we have a very high capacity task network, the high capacity task network had an inbuilt capability of extracting all the relevant information from the images itself. So that's why for the high capacity network, the AI-based processing or the virtual staining did not essentially help to improve the task, and in some cases it degraded. But for the lower capacity one, since it did not have all the capacity to extract the information, the processing was just working as a preliminary step to help the low capacity network to extract more information. So this is how the task utility of understanding any medical image quality or biomedical image quality is basically tied with a very old information theory in different mathematics and different engineering, which is used in different mathematics engineering topics before, that your task utility is tied to the information content, and this cannot be increased with the processing. But based on how you're solving the task, it sometimes the processing might help, but fundamentally not increasing the information, but making information much easier to access by a low capacity downstream network. So yeah, in a similar direction, we are currently working on doing a more deeper theory of coming up with some information theory based matrix to understand the task utility in a better way. So I guess that's all from my side, and this is my lab and my lab mates and advisor Mark Anastasio, who is a prof here in UIUC. And I'll be happy to take a question for remaining 5 minutes I have. Thank you.
Thank you so much. Very exciting. And what you say about cells can, of course, apply to populations and clinical syndromes and whatever. And it can be applied also to the other aspects, namely of informatics. I mean, apply the best mode of information, the efferent way. So, this was very exciting, really. And I think one of the importance of artificial intelligence is the kind of authority it has, because one tends to trust these kinds of analysis and where you can really improve our way of treatment in many areas. The cells, of course, is a good model, but I think we can have it taken into other models too. And thus I wonder, are there any questions or ideas coming from the auditorium on this very exciting chapter?
Yeah, I have just one query. Like, while training the models, so the data that you have, is it like, is the data, number of data on which you do the training is significantly large, or it's very limited data?
So it's basically, so if you look at the left graphs for both the cases, like the top left and the bottom left. So these are around 15K training images. This is a lot because this is the data we are generating in our experiments with our collaborators. So it's around total 15K in terms of image and the labels.
Okay. Okay, let's see any questions on YouTube if anyone has. Not yet any question. So if any further question would be available, I will certainly share with you.
Thank you so much.
Thank you. Thanks again. And I'll be thinking a lot about this, I can assure you. Now it's the final presentation, which is also very exciting and bringing high up in the abstract and complex. And it's about making and breaking quantum supremacy. Really a big task. And it will be presented by Sumil Ghosh, also from USA. And please welcome.
Hello,
and
everyone.
start talk.
Sure. Let me try to share my screen. Yeah, can you still see my screen?
Yes.
Yes, okay.
Very good.
Okay, so today I'm Shomik. I'm a PhD student in Chicago. Today I'll talk about quantum advantage, making and breaking quantum advantage, which would be like a broad summary of one of my recent papers. So before I begin, before I go into the technical parts, let me give you a little bit of background about myself. Like I mentioned, I'm a PhD student in Chicago, and I'm a theoretical computer scientist. more specifically, I'm a complexity theorist. But I am slightly different from like traditional complexity theorists in that I work at the interface between theory and applications. In some sense, I use computer science to shed new light on physics. And over the last many decades, physics has been the driving force behind quantum computing. All the advances have primarily been made with an intuition that has been honed in physics. And in some sense, my research is kind of like a mindset change. In some sense, I'm asking whether direct concepts from computer science can guide physics. Can we use computer science to prove new results in physics? So what sort of questions do I care about? I care about problems that are both theoretical and experimental. Like questions like, can computer science tell what is measurable in quantum theory and what isn't? What you can feel in the real world and what you can't feel when you are trying to implement quantum mechanics on a large scale. So I have some works on this, like pseudo-entanglement, pseudo-magic. Check them out. But what I'll talk about today is slightly more applied. And the question is, can we use concepts from computer science to design the next generation of quantum supremacy experiments? And the idea is to design an experiment with some nice features, where verification is faster than simulation. I'll go into the details of this very soon. But before that, what is quantum advantage? The goal is to perform a task with a quantum computer that would take a classical computer a very long time. For instance, like recently Google performed something with a quantum computer, with their quantum computer in a few seconds. And their claim is that any classical computer would take 10 to the 27 years to perform the same task. And not just Google, numerous quantum advantage or quantum supremacy claims have been made, like starting from the 2019 experiment by Google. Like with the Sycamore chip, there's been USDC, Xanadu, Google again, USDC again. Also many other startups, a lot of claims about computers achieving quantum supremacy. But why care about, say, experimentally demonstrating quantum supremacy? So in some sense, like I said, this is a test of physics. So there's a hypothesis in computer science that any computer can be efficiently simulated by a classical Turing machine, like this abstract model of computation that theorists have come up with. But these quantum supremacy experiments are an experimental test of violations to this hypothesis. So the existence of quantum computers violates this theoretical hypothesis. And the motivation is to perform efficiently any task that would take this abstract computational device, the Turing machine, a lot of time, exponential time. That's one reason to care. But yeah, so like I mentioned, there's been a lot of quantum supremacy experiments that have been developed, but they all have a big gap. What's the gap? Say Google comes up and says that a classical computer takes 10 to the 27 years to simulate whatever the quantum computer did. So this is like Google's claim. Well, then one retort to that claim is that verifying the experiment, like classically convincing someone that whatever Google did is correct, verifying also takes 10 to the 27 years, which is as bad as entirely simulating the entire experiment classically. There's no gap between verification and simulation. And why care about this gap? the reason to care is that there are many practical applications that have been proposed. For instance, we know that quantum computers are good for many cryptographic applications. Like there are these primitives in cryptography that to generate random numbers, to do quantum secure cryptography. And because of some of my works and some other recent works, we know that Google's devices are good for cryptography, for instance. And they have nice cryptographic guarantees. They can be implemented. Google already has the hardware. You can implement them in the near term. They have nice guarantees. But the problem is, none of these cryptographic applications are near term because of this problem that verification, like verifying that the cryptographic experiment was correct, takes as much time as full simulation of the entire experiment. I want to pause and stress the importance of this application here, because one reason to be fearful of quantum computers is that they are going to break cryptography. They're going to break your bank accounts and credit cards. But it seems like, from recent research at least, quantum computers are also good for cryptography. So in some sense, quantum computers with these protocols, if they are practical, if they can be made practical, will be solving the very problem that they will have themselves created. So it's very interesting. But like I said, these protocols are not practical because there's no gap between verification and simulation. And this is what prevents them from being implemented. Like, why can't Google just implement these protocols, these cryptographic protocols right now? Why do we not have any useful applications of quantum computers? It's because that there's no gap between simulation and verification. Yeah, like I mentioned, the reason things are not practical is because verification is too costly. And that's exactly where we come in. We have a new experiment. But before that, let's recap the old experiment. So what do people do? Like, how did Google claim quantum supremacy? The idea is to first generate a quantum circuit. Like, say you have a 2D lattice. The white dots are qubits. The lines are gates. So you have n qubits, and you have a bunch of gates. And you randomly sample these gates from some distribution. And so you get a circuit like this at depth d, and you have some input state, say 0 to the n, and you apply this circuit that you randomly sampled on the input state. And then you do something called measurement in the standard basis in the end. They have a starting state, apply a circuit, and do a measurement. And this is quantumly easy. It's kind of just implementing a quantum circuit. Have a starting state, have some circuit that you do, and then implement. This is quantumly easy. However, there's strong evidence that this is classically intractable. And so this is like a good candidate to demonstrate quantum supremacy. And this has now been implemented. So 53 qubits, 60 qubits, we keep having larger qubit numbers. Like Google has the best hardware right now. And so this has now been implemented. And this gives you like a task, like I said, where you have quantum supremacy. But there's a problem. And the problem is that verifying is too costly, like I was saying. Why? Because the output distribution that you get. So when you measure, think of measurement as like sampling a string from some probability distribution that's created by circuit and the input state. There's like very small signals, like so the distribution is very close to being uniform. And uniform distribution is like fully flat. There's like very small like wiggles in the distribution, which are the quantum signals. And finding that out is extremely hard. To find those wiggles, you need to simulate the entire experiment classically from step 0. And that's the problem. For instance, this is already manifesting. For Google's 105 qubit experiment, verification is already a hard task. It's no longer feasible. And so maybe the next step with the new hardware that we have is to design a new experiment where verification is easy. So like I mentioned, for like Google's case, you have a flat distribution and you have some small wiggles. So some small deviations from uniformity. So, but what if we have something different? What if we have like slightly more wiggles? If we have some sort of a peakedness, like some peaks, where like say there's some outcome in the distribution, some string, where a lot of probability mass is placed. So when you sample from the distribution, you're overwhelmingly likely to see that one string. And then you can just verify by checking if the samples all are consistent with that one string or not. So you basically put a lot of probability mass on that one outcome. And you make the distribution very peaked. The problem is whether it's possible and whether it's possible to do it without classically spoofing the entire setup, without giving classical computers a lot of information to now like destroy the quantum supremacy. And like I said, if we have a lot of probability mass on just one outcome, like think of all the probability mass to be like centered around say 0 or 1 or something, like one deterministic string. If we just repeatedly sample and see that one string, then we can just verify based on that information. But yeah, like so verification is easy, but designing this experiment such that it's classically hard to spoof, that's hard. And what do? We kind of solve this problem where we have a new experiment which is peaked, where verification is much faster than simulation because of peaks. Like we have a way of making the distribution extremely peaked on one outcome. Well, the RC has provable hardness guarantees. And all the applications that you suddenly now have, like that you suddenly have postulated for random circuits, are all now practical or feasible. They're within the realm of possibility in the next 5 years. All these cryptographic applications and everything that you had postulated. And so, and our scheme is based on error correction. And so it's more than a quantum supremacy experiment. It's more like an experiment that you do with error correction, like en route to maybe building a full quantum computer. It's kind of like something you can do with like limited powers that exist right now. And what is a circuit? I won't go into the details of it. We use like coding theory, and then so let me just show the circuit. So we have some initial state initialized into like zeros and some pluses. These are like states of a qubit, like 0 or 1, and plus is like a superposition of both 0 and 1. We have these zeros and pluses. We have some encoding circuit, and such that the state that you have here after the gray box is the code state of some error correcting code. If you want to abstract it for now, just say that this is some simple state that you prepare by like a simple quantum circuit, almost classical state. And then you have these layers of rotations, these pink boxes. Like you have some rotations that rotate the state into some direction, onto some direction, depending on the angle theta. And then you have some measurements. And that's it. This is the circuit. It's very simple. You just have an encoding circuit and some layer of measurements, and then you're basically done. And the thing that we prove is that this circuit gives you a peaked distribution that is also classically hard to sample from. So you have like verifiability, like fast verifiability, but you also have hardness of classical simulation. This is the fast time verification is much faster than simulation. And for instance, if you choose parameters, this is an experiment that experimentalists can do like now, like right now, on say 120 qubits, which is like very reasonable. Like the most powerful quantum computers have qubit numbers within this range. You can do it with 120 qubits and like the noise rates that you have now. Like it's very consistent. It's very appealing as a like an experiment that you can do right now. And thank you. These are my collaborators. Bill is my like PhD mentor, and these are my collaborators of the work from different places. Thank you.
Was that? Yes, very nice thought again, and a lot to think of here. And it's getting a bit fussy, this to compare such entities involving so many things. So what about the conclusion power of the general applicability of these measurements, so to say?
Yeah, the conclusion is that we now have a scheme which gives you useful applications with quantum computers. Yes. I guess like one problem that many skeptics point out is that quantum computing does not have useful applications, unlike machine learning.
Yes.
And one reason it doesn't have that yet is because verification is very costly. And this is like the fast step towards getting like useful applications with quantum computing. Like say you can say when quantum computing is popular enough, say you can buy something from Amazon, like a quantum computer. What can you do with it? It's like the fast step towards getting something useful done with that quantum computer that you can buy from Amazon.
Yes. Well, it's fascinating, really. There must be questions about this now, which I call. Please welcome with questions.
Yeah, I have just one query. Like as you mentioned, the cost for simulation might be more than the cost of verifying here, right? So
yes, no, like that's usually the case. This is the protocol. This is the fast protocol, but this is not the case. Like the cost for simulation here is more than cost of verification. The fast protocol, but this is the case. Okay. Whereas before, simulation and verification had the same cost.
Okay, so that means overall the cost has been reduced. Like if I compare the simulation plus verification, then the cost has been reduced in your case with the same sample size?
That's right. Yeah.
Okay. That's quite interesting. Idea could be like, as you mentioned, could have more application in real life that way.
That is the hope, yes.
Yeah. Okay. So any other question? Let's see on YouTube. Any question?
Well, of course, one question is, has technology advanced to cope with, so to say, expectations? Is quantum computing coming to fulfill its potentials?
Yes. It is going to come in the next 10 to 15 years, I think. I think the last few years I've seen a lot of progress on the hardware front. Yeah. So right now we have a really good hardware. For instance, we can implement this scheme that I mentioned. We are talking to experimental groups to implement this scheme.
Yeah.
And so the current hardware is good enough to do these more advanced demonstrations. And the hope is all the companies now have a roadmap like IBM, Google, and many of the startups. And the roadmap says that within 2030, they'll probably have a very powerful quantum computer ready for public use. And like once we have that, I think a lot of applications will unlock themselves as people like start using quantum computers and try to see what they're good for.
Yeah.
So
Well,
I have no idea
thank
about how much time usually it takes to run one experiment or one simulation in terms of seconds, hours.
So it depends if the circuits are very optimized, and that I think is the hard part, like pre-processing. Then I think it takes a few seconds if you have the right hardware.
Okay, but pre-processing is quite. It might be taking more time, or
No, pre-processing is like pre-processing takes a lot of human time because you need to be clever with optimization algorithms, and you need to be clever about how to get the most optimized circuits and all that. But like there's no theoretical barrier to anything. It's more like being clever with your choice of like parameters and all that.
okay, yeah. Thank you.
Okay, now I have one question.
Yes,
Hello?
please.
Hello. Actually, my question is the quantum computer is a threat to the new era? Have any comment?
Yeah, good question. Yeah, so like the reason people believe that is because quantum computers potentially break cryptography. Like there are like algorithms that break crypto systems. So maybe like credit cards or like bank accounts or passwords might be at risk. But the point is, quantum computers can themselves solve the problem that they have created in the sense that you can base new cryptography of the modern age, on principles of quantum computing, which is also what I have done and some other collaborators have done in the recent years. So you can base cryptography purely on fast principles of quantum mechanics, which would be secure against quantum computers. So if you like move away from present cryptographic standards to something more suitable for the modern age, then everything is fine.
Okay. So it may be threat, but if you have any other algorithm which is also something new, then it would be combated. Is it so? Not.
Yes, that's right. That's right. Yeah, that's right.
Thank you for your lecture.
Thank you.
Yeah. Yes, thank you really very much. You really touched our minds here, and we look forward and wonder how does it will look when it comes to the supermarket, the quantum computer.
Sure. Yeah,
Are
yeah,
you
yeah. That
designing some? Yes. Anyhow, it's going to come, and that's a good idea.
Yeah,
and
yeah,
now,
it's going to come.
Yes, so thank you. And it will be cheap or rather expensive.
I
It's
think
hard to say.
it will follow the same trajectory as classical computers. So it will be like very expensive in the
Yes.
beginning, but over time the curve is going to like go down, the price curve.
Yes.
But it won't be like for general purpose computers as we use, but whether the computer for general
So far,
purpose.
no. So far, no, but the curve there could also be like classical computers, but classical computers, when they were first built, were not general purpose. They were only used in like labs or like very advanced like scientific like research. But with time, I think the point is that if you have like enough like with time, like if you have enough like curiosity or like interest, then you can miniaturize the devices and make them cost effective depending on how widely used that like the devices are. So the same thing happened with classical computers, but the 1950s machines were very bulky and not fit for like public use. But then Apple and Microsoft and all these companies came in and they made like laptops, PCs, and like small computers, which were like more suited for public use. So similar trajectory can happen for quantum computing, but that's far into the future at least.
Thank you.
Well, thank you so much. And this will also
Thank you.
end our session. I think I have one little general comment to make. You must all wonder about my rather terrible appearance here with wounds and hemorrhages and so on. And what happened? Yes, I slipped on the floor and hit the little edge there. So, but I can assure you, with all help of medical informatics and also perhaps artificial intelligence here, that it's being taken care of and in the process of healing. So that will close my presentation here. Thank you so much again, all speakers. You have made very much interesting talks. That's my opinion. Thank you.
Thank you, Eric, for chairing this session, and we are very sorry to hear that some injury has been happened to you, and might be like, as you mentioned, it's a live demo of how AI, ML, and medical
Yeah.
advancement has taken care of your healing process.
Yeah.
But please take
Yeah.
care. You are our motivation for working hard. At this age, you
Yes.
are so young. So please continue with all the energy that you have, and
Yes.
transmit to us also. Okay, so that's the end of the
Yes.
today's technical session 4, and we are first thankful to Professor Eric Trell for chairing this session, and I'm thankful to all the speakers, starting from Gurel, Gabriela, Carl, Shoro, and Shomik for joining with us, and it was really very informative. And tomorrow, again, we are going to have the similar session. It will start with 3 parallel session of paper reading, and then followed by the data science workshop, and then followed by, again, the invited talks. And at the end, we'll have the valedictory session. But just again, I just want to mention that our first day's YouTube hit more than thousands views. So just within one day, it became 1,000, more than 1,000 views. People, we are thankful to our viewers. We are thankful to our speakers. We are thankful to all the persons who are helping all the day. Thank you very much, and hope that for today's view, we will get something like that, so that I'll be able to exactly how many hits that we have. And I must say that goodbye, and see you tomorrow. Okay.